Hello, this is the Group 1 Turn Project presentation on designing the unmanned area system. During this presentation, we will introduce you with the team members, followed by the purpose of the project, customer needs, design matrix, US comparison, final design, flight test results, and finally a summary for the agenda. Our team member consists of 3 people: Elizabeth Talburt, Devon Barragan, and Soemoe Oo. First, the purpose of this project is to assist NFS, the National Forest Service, to explore the option to use an unmanned area system to locate missing hikers. The team has conducted experiments to support the NFS with designing a UAS that fits their needs. First, we have to look carefully for what they need. The NFS would like to utilize remotely pilot vehicles to aid in search and rescue. And the vehicle type that they want has to be a slow-moving vehicle, must be a small size, it will be able to operate at low altitude, typically less than 3,000 feet, has to be easily transportable, will be able to navigate the low mountain terrain, able to operate under a wide range of weather conditions, and able to operate during day or at night. So the team first must have come up with the design metric. For the design metric, Devon will continue doing on presentation.
Before exploring the options available within the Embry-Riddle Hub Assembly Lab, our team came up with the following design metrics that aligned with the needs required for the National Forest Service. The first requirement was that the vehicle should weigh 50 pounds if it was going to be moved by a one-person team, and if it was going to be moved by a two-person team, it should weigh about 100 pounds so that it's easily transportable. This weight factor was based off of a study by the Human Factors and Ergonomics group that concluded that 50 pounds is a reasonable weight for the average person to carry. The second requirement was that the dimensions of the vehicle should not exceed 4 feet by 5 feet, and if it was larger than this dimension, then it should have the ability to be folded to fit within the constraint so that it too is easily transportable yet small in size. It should also be waterproof so that the vehicle could operate under a wide range of weather conditions. For example, if it was raining, it could still be able to fly. Another requirement was that it should have a high intensity lighting using a 1000 watt LED lighting system or an infrared lighting so that it could pick up on heat sensors on things on the ground so that it was able to operate during the day or night. Another requirement was that it must not go over 100 miles per hour, so this would require it to be a slow-moving vehicle. And then we also came up with the shuttle radar topography mission, and this is the second global elevation data that offers a worldwide coverage of void field data at a resolution of 1 arcsecond, and it provides open distribution of this high-resolution global data set. This need that was met was that it would be able to operate at a low altitude less than 3,000 feet. And lastly, we came up with the shuttle radar topography mission so that it can navigate on a low mountain terrain. So after we came up with those original design metrics, we came up with a revised design metric. And the ones that we changed were the last two. So we came up with the laser altimeter so that it could still operate at a low altitude less than 3,000 feet, and it would also have a manual control system so that we can navigate through low mountain terrain. Here we have the total weights of the different power systems, and it can be noted that the Gannett rotary wing was too heavy, and so it was immediately excluded as one of our design options. The turn fixed wing was 22 pounds with just the power source, and we found that the lightest and the easily transportable vehicles would be either the octorotor or one of the two quadrotors. Ultimately, we decided on the Condor octorotor, and this was due to the redundancy in the motors. If one of the motors were to fail in the quadrotors, it would cause the air vehicle to crash, as opposed to the octorotor, which has 8 rotors that would still be able to fly if it lost one of its other rotors. This gives the octorotor the ability to operate under various weather conditions. And so, with the UAS comparison, this is a summary of why we chose the octorotor and why it fit our team's metrics for the NFS and rescue vehicle. The team varied the subsystem of the octorotor to yield the optimal combination of sensors, camera, antenna, and other subsystems, and the chosen design of the vehicle consists of the X8 black electric motor, manual control, infrared sensor with gimbal, dipole antenna, ERA 5600 battery, GCS trailer with large dish, and IMU/GPS sensor.
Our final design, so we had 3 designs that we varied the different systems to test the Condor octorotor, and we settled on design 3. So design 3 had 8 black electric motors, manual control, an infrared sensor with gimbal, laser altimeter, dipole antenna, ERA 5600 battery, a GCS, so ground control station trailer with a large dish, IMU, which was an internal measurement unit, and a GPS system. This is a screen capture of our flight test. Since it was a manual control, it was easy to navigate through the mountainous terrain, and highlighted in a red box is the silhouette of an animal. It looked like a bear. And because we were using an infrared sensor, it was easy to spot the silhouettes of animals. So it would be easy to spot the silhouette of a person. And this is due to the fact that the heat signature of the terrain is dark. And the heat signature of, say, an animal, or as you can see in the background, a fire, is bright white. So the contrast between the darkness of the background and the bright white signature of any living thing that it happens to be in the forest will allow us to have clear sight if there was a missing hiker and if they were somewhere in the forest. So this is a summary of our findings. So we used the Condor octorotor and the 8 black electric motors fit metric fit metric 6 and 7. It allowed it to be able to operate at low altitudes, navigate through low mountain terrain, and it also met metric number 3 in that it could operate under a wide range of weather conditions. And again, that was because of the redundancy in the motors if there was a motor failure due to weather conditions. The manual control also met metric 7, which was the ability to navigate through low mountain terrain. The GCS trailer with large dish also met needs 6 and 7, so being able to navigate through that mountainous terrain, you need a wide range for your signal, and signal transmission with the GCS trailer was very strong. The infrared sensor allows the UAS to be able to operate during the day or night, which is metric 4. The laser altimeter meets need 6, which is the ability to operate at low altitude. That laser altimeter provides feedback to the UAS and to the person controlling the UAS. It provides information on how far that vehicle is compared to the ground and if evasive action should be taken if the vehicle is flying too low. The GPS module allows trackers' locations to be precisely noted. The battery has to do with the fuel, so if it were to be operating under an engine that required fuel, then that would have an impact on the weight capacity. And the IMU, so the internal measurement unit, addressed the need to be able to operate under different weather conditions. So that would provide any information on if there was some sort of damage or errors in the control system or systems of the UAS. The IMU would pick up on that and be able to send feedback to the controller. So they would note that if there's any changes to the UAS because of rain or the weather, that information would be available to the person controlling the UAS. And references for our project are included. So thank you for listening to our presentation, and I hope you enjoyed our design project.